In this video, we're going to start talking about the second derivative. So far we've taken a single derivative, and we called that the first derivative, or f prime. Now we're going to start taking more derivatives than that, and in particular in this video we're going to talk about what the second derivative has to say about the graph of a function. So thankfully this connects well with the stuff that we were doing before the break. So I think I will take the opportunity to review the stuff that we were talking about right before the break. So remember, the last thing that we talked about was the first derivative test. And the idea behind that was maybe we might want to maximize the y value that our function takes on, or minimize the y value that our function takes on. So notice that if I look up here at this peak, this is the largest y value that's attainable anywhere on the function that I've drawn so far. So I might want to maximize this function. Maybe this function represents something like revenue, something like that. If I wanted to maximize that, then I would want to be sitting here at x equals a. And conversely, if I wanted to be minimizing this function, then I would want to be down here because this is where the minimal y value is attained, at least in the part of the function that I've drawn so far. So remember, the first derivative test told us that we could start finding candidates for these local maxes and local mins by noting that both of these are what's called a critical point. So remember, a critical point is where the derivative is 0. So over here on the left side of a, the derivative would be positive, and on the right side, the derivative would be negative. But notice if you're sitting at the top of the hill or at the bottom of this valley, the slope is exactly 0. So in other words, the derivative would be 0 here. So at the peak here, f prime equals 0, and at the nadir here, f prime equals 0. So that gives us a way of looking for these points a and b. We called them critical points. Those are just the points where the first derivative is equal to 0. And we could identify whether those critical points were local maxes or local mins by making a sign chart for f prime. So I'll just quickly remind you what that looks like. We made a little number line, and we wrote down all of our critical points on that number line. And then we also noted what the derivative sign was on each of these subintervals. So there are 3 subintervals here. Notice that if you look to the left of a, here the derivative would be positive. So the derivative was positive to the left of a, the derivative would be negative to the right of a, and then the derivative is positive again once we cross over b. And then based on this sign chart, we could decide whether a or b were local maxes or local mins. Now that is clear just from the graph. So we know that a is going to be a local max and b is going to be a local min. But you can also tell that from this sign chart by just noting that if you look near a, the slopes go from being positive to 0 to negative. So this is what the graph has to look like near a. And then conversely near b, the slopes go from being negative to being 0 to being positive. So b will be a local min and a will be a local max, like we see in the graph. So in the second derivative test, we're going to talk about a slightly faster way of determining whether some critical points are local maxes or local mins, and that has to do with the concavity of the graph. So maybe notice here, the shape of this part of the graph is sort of a bowl that's facing down, and this shape is an upward-facing bowl. And it turns out that the second derivative will tell you whether you're looking at a downward-facing bowl portion of the graph or an upward-facing portion of the graph. And we call this property of the graph the concavity of the graph. So this first portion is called concave down, and the second portion is called concave up. And we'll talk about that in this set of notes. So here, these left graphs are both concave up. So notice that here you're looking at maybe the right side of an upward-facing bowl. Here you're looking at the left side, but both of them are concave up, even though the first derivative is positive in the upper graph and negative in the lower graph. So all that we care about here is just the curvature. And in this case, you have upward curvature for both of these drawings. And then on the right side, we have negative curvature or negative concavity for both of those drawings. Okay, so here, notice that graphs that are concave upward will correspond to those local mins. So if I give you an upward concavity that looks like this, then any critical point that occurs in an upward concave graph has to be a local min. And conversely, if I tell you that you have a critical point in a concave down region, then that critical point must also be a local extrema, but it has to be a local max. And the nice thing about this concave up or concave down is that it's detected entirely by the sign of the second derivative. So maybe let me go up to this drawing again. Notice that in this picture, f being concave up is the same thing as saying that the slope is increasing. So here the slopes are increasing. These slopes are getting more and more positive. The same thing is true down here. These slopes are getting closer and closer to being positive. So concave up is the same thing as saying that f prime is increasing. But as we saw with the first derivative, saying that a function is increasing is the same thing as saying that that function's derivative is positive. So in both of these, the concave up behavior is the same thing as saying that f double prime is positive. And similarly, if we want f prime, that function, to be decreasing, then that means that that function's derivative is negative. So in other words, the derivative of the first derivative will be negative here, and we'll call that the second derivative. All that means is that we're going to take the derivative twice to compute the concavity in these situations. So for example, just to make up a simple example, if f is equal to x squared, then we know how to compute the first derivative. That would be 2x. But the second derivative is just the same thing. So we're just going to take the derivative of the line right above to get the second derivative. The derivative of 2x is just 2. And notice that in this case, the second derivative is 2, and that's a positive number. So that would be a concave up picture. And we already know what the graph of x squared looks like, but it is indeed a concave up picture. And it has a local minimum down here at the bottom of this little valley. Okay, but we could detect the concavity of that picture by just noting that the second derivative of this particular function is positive. So we're going to use that to our advantage whenever we're talking about how to graph particular functions or how to detect local maxes or mins. So first we're going to focus on the graphical interpretation here. So let's say that we have this graph of f, and we want to determine the signs of f prime and f double prime over this domain. And we will then use that to talk about the concavity and inflection points of this function. So the concavity we've already talked about. The inflection points are just the places where the concavity changes. So if there's a place where the function changes from concave up to concave down or vice versa, that'll be an inflection point. Okay, so first, let's just talk about the signs of f prime. So f prime is going to be positive. Remember, that just means that the slope on the tangent line is going to be positive. And it looks to me like that happens between negative infinity up to negative 2. Because in this region, you have positive slopes. And then similarly, we start having positive slopes again over here on this side. So that would be from 2 to positive infinity. Now, whenever you report when the derivative or second derivative is positive or negative, you're just going to report that in interval notation like this. And you're always describing the intervals in the domain. So in other words, the x values where this property holds. So the slopes are going to be positive for this set of x values. And then similarly, if we want the derivative to be negative, it looks like that happens between negative 2 and 2. Okay, and then we can do the same thing for f double prime, but remember that for f double prime, we're looking at the concavity of this function f, and f double prime will be positive if you're looking at some portion of the graph where you're concave up. And it looks to me like this portion of the graph is the concave up portion. So I would say that this graph is concave up from 0 to positive infinity. And it looks like f double prime will be negative over here on this other side. So here we would have negative concavity. So f double prime will be negative if you live to the left of 0, which would be from negative infinity to 0. So now we've determined the signs of everything to verify this concavity. It'll be concave up in this region, and it'll be concave down over here on this side. And lastly, we wanted to find any inflection points. In this case, we know that we go from being concave down to being concave up only at a single point, and that seems to happen at 0. So there is an inflection point. The inflection point is at x equals 0, and there's only one inflection point. So we'll do a few more examples of that in the next video.